Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, we are here now where we want to go into the scanner generator now. Now we see the scanner generator wherein we just saw the Lex programming and all those things. Now let us see how our Lex works inside, or any scanner generator like Flex, or in case of Java, or JFlex or something else, wherein we see that we have a regular expression, uh, okay, which represents our regular lexical specifications by regular expressions. Then when we have regular expressions, first thing what our scan generator does is it converts it into the NFA using the Thompson's construction. Okay, that will be the non-deterministic finite automata. Now this non-deterministic finite automata is converted to the DFA using the subset construction. So typically these guys are now our subbars, because we're gonna in this video we're gonna concentrate on the Thompson's construction. Then we in the next video we'll go from subset construction where we see NFA to the DFA, and then we're gonna minimize it into the minimized DFA, and then we have simulations, DFA simulations, and we will try to convert it into if it is a Lex in a C program, or if it's JFlex a Java program, whatever it is, we can convert it into some kind of program, which will be implementing our lexical analysis of our compiler. Right? This program actually is our lexical analyzer, which takes up the string and converts into that the tokens. So because now this guy will have the character stream on this side, and this program will convert this character string into the program. Okay, now what we do is we will concentrate in this video on this part only. Okay, so that is the Thompson's construction. That is how we convert from RE. So we have here with my pen, we got the regular expressions, and we want to convert this into the NFA using the Thompson construction. Before dealing with this, we would like to explore what is this NFA, and how it differs from DFA, and what differences are there, right? Okay. So broadly speaking, we said our automata is basically either a deterministic one, DFA, or it is the non-deterministic, called simply the NFA, non-deterministic finite automata. So we are discussing actually the finite automata, right? And we saw there are two types. Now what is the actual difference is that in NFA, basically the major difference from deterministic is that we don't know exactly where we want to go. What does that mean is, in DFA we had exactly one path. For example, you're on a state, for example, some state X, for example, and on input A, you will exactly land into some state, say Y. But in case of NFA, if you are on a state X and you take a state A, it is not necessary that you will land into this state Y. You may go into the state Z as well on taking the input A, or you may go into the state Z as well, say W as well. So you can have a multiple states. You can go to the you have on an input A, you have many choices. We'll discuss this in detail. And then you also have a major difference from DFA is that you here the absent transitions are not there; they are absent. But in NFA on Q1, you can go into some state without taking any input. What does that mean? We will discuss this and to understand this. Okay. Precisely speaking, actually, NFA has three features when compared to the DFA. One, its ability to take step without reading any input symbol. So you're not reading any input symbol, but you can still have a transition. And you may have a no transition on a particular symbol. You have a symbol, you have an input, but you don't have a transition. So these are two contrasting things. And third thing is, which we just discussed, so that ability to transition to more than one state on a given symbol. Okay, let's now try and understand. Now let's take a first thing, what's called as an epsilon transitions. Now in epsilon transitions, what we're talking about that is that you are having a transition without reading any input symbol. So you're not reading any input symbol, but still you have a transition. To actually understand properly, we may see a example of color, COLOR, and if you see the British, you have this thing, COLOUR. So these are one and the same thing. Okay, color, COLOUR. If you write COLOUR or you write COLOR, American or British, they are actually the same thing, which means the color. Okay, now when you are trying to recognize these things, you have to recognize both. Okay, if a user has written the color, or there is a color COLOUR, the both of these need to be recognized. So how you will have a if you see a transition diagram for this, so we have on a state A, for example, and when a capital A, okay, then you saw the C, then you saw the O, then you saw the L, for example, then you saw the LO, then U, and then R. Okay, and then you say, okay, it's a final state. So COLOUR, this is this guy, right? But maybe on this U, if this may be absent, okay, if this may be absent, still it is a valid string. So what we do is here, we have here an epsilon transition. Actually, you should show the arrows here, right? Okay, for a transition to be happening. Okay, so here you have an epsilon transition. So that means that if you are on an O and you don't have the U, for example, you still move on to this state. Okay, now you have to use this way, because if there may be U to go into this state. Okay, say this is A, B, C, D, E, F, and G is my final state. Okay, so you from E to the F, you can move it either from the U, or even if you don't have the input, you can still move from E to F, because from the F you can have an R to go to the final state. Okay, so that means you can go from a particular state to another state without taking input. That's what epsilon means. Okay, but this can't happen in the DFA, because DFA epsilon transitions are absent. Okay, does it make sense? Now we are on the next thing, which says that a state may have no transitions on a particular symbol. What does that mean? For example, I can think about another. Here. To the right pen. For example, you are trying to accept a 1. So, for example, you are trying to accept string 1, well, input 1. Say, for example, you are on a state A, and on taking 1, you go to the state B. Okay, and if you have 1, you accept it. For example, simple as it is. But now, if on A you are getting the input 0, so what is happening here? So even though there is an input, you are having no transition at all. Okay, it's again not in a DFA. In DFA, if you have the input symbols, for example, for the input, you are talking about the input 0 and 1. Okay, for on every state you have to see what will happen at a 0 and what will happen at a 1. That's the DFA. But in the NFA, that you are having an input 0, but you have having no transition at all. Okay, so this is my second point, that where a state may have no transition on a particular symbol. Okay, and then the last one is that you can go for having a multiple transitions. Okay, say for example, if we see an example here where we want a language in which string ends with the 0, 0, 1. What do you see like that? or something else, or ends with 0 1 maybe, or something else. So if my string has to end with the 0 0 1, actually all those strings which ends with the 0 0 1, all those binary strings which ends with the 0 0 1, then firstly I will have a 3 states. Okay, on this state I go to the 0. If it is 0 I go to here, if it is 0 I go to here, and if it is 1 I'm gonna accept it. Okay, and in the beginning can be anything, because I'm saying it should end with this thing. So in the beginning there could be anything. So here if it is 0 or it is 1, I can go to, I will stay on this state. Say this is state A, B, C and D. So if in the beginning it comes 0 or 1, 0 or 1, you can any zeros or ones, you are staying here, no problem. And when if it ends with zeros, you can go to B, you can go to the C on this 0, and on 1 you go to the B and you accept it. Okay, but if you see here on a 0 here at the A, you can go to the either state A or you can go to the state B. So that means you have a multiple transitions. You know, I mean, you have a transition to more than one state on some input. Okay, 0. For say, for example, here 0. One more thing, if say on a B, you have after the 0, or here at a C, if after getting the 0 0 here, you're on a C, now you are getting the 0 again, because there is no transition of 0 from the C, so it dies. What it does is that string will be rejected. So that means there may be the strings which are rejected, and there may be strings which are accepted. And if at all we have a one path which takes us to the final state, we say this is accepted. That string is accepted, because maybe we have a string. Say for example, we have a string called 0 1. Okay, 0 0 and maybe 0 and maybe 1. Okay, let's take this input. Say maybe we have on an A. If we choose from 0 to stay on an A, we can be here. After 1, we chose stay on an A, and we take this path and go on an A. We stay on A. Okay, we are on an A now up to this moment, and after that we take a 0. We can go to the A on also, or to B also. Maybe if at this position I go to the B. Okay, so I'm here at a B. Now at B I'm having an input 0, and I can go to the C, because I have only way to go to the C. But at the C I don't have a 0 transfer for the 0, so here this will be rejected if I take this path. But say for example I take it again, I go for A as a 0. When I take a 0 and A, I go this way and stay on A on 0, and I take a 1, and on a 1 I stay on A. Okay, then I take 0, this 0, and I again go this way, so I stay on A. Now here I take again 0, but this time I decide to go to the B, so I go to the B and I take this 0 now, and I go to the C, and I take 1 and I go to the D, and it's a final state, so I accept it. If out of many such ways I go, and one of them is leading me to the accept state, so I will accept this input. This is in the NFA we have to scan all those things, where I will have at least one path which will take me to the acceptance state, that is D. In DFA we usually have only one way to go, but in NFA we have many options. We have to see which option we want to go. For example, in the chess board, if you are on a chess, you're playing a chess, for example, and you are here, and you can go many ways. Okay, you can go here, you can go here, you can go here. Sometimes you can go on this side and go this side. So there are many options to go for chess pieces. For many pieces, you have many kind of movements which can take you. You have to take it. You can go in many ways. Okay, so this is the NFA. And the DFA, you have only one way to go. Our computers work more like a DFA, but NFA is more simple to design than the DFA. From RE to NFA is much better than from RE to DFA. So if we little sum up from the DFA to NFA. So we have here as you know, from a state is to a single particular next state. So that's why it's called deterministic. But here you have multiple options. That's why it's called non-deterministic. So absent transitions absent. Here we have backtracking is allowed in DFA, okay, but not in NDFA. It's not always possible. It requires more space. That is important. It requires less space. So a string is accepted if it goes from a start state to the final state, okay. But here the string may die out in the middle. But if there is at least one of all the possible transitions and is in the final state, we say okay, it's accepted state. Okay. Now then we need to go for a final formal definition of the NFA. So if you see the formal now the formal definitions, we already have done it for the Automata. So it is going to be the quintuple or five tuple. That is, we need to have a Q, we have an input symbol, okay, then we have a delta as a transition function, then we have a Q naught, and we have an F, the final state, and this is all same set of states Q, input symbol, okay, and then delta is a transition function which is different in NFA than in a DFA, and Q is the start state, and F is a set of final states. We know that everything we know, okay. So we have a formal definition here. So we say that it belongs to the phi, it's a quintuple. Q is a finite set of states, okay. Then input symbol, that's a finite alphabet. Then we got a transition function that is from a state Q, and you have an epsilon also here in the input. So if your inputs are, for example, 0 and 1, you also have epsilon here if it's NFA. Okay, so that's why we are our input symbol alphabet, we are doing union it with the epsilon also. So it will land into the power set of the Q. That is the difference. Okay. In case of DFA, if it was your transition function, you had some input symbol, okay, say some whatever the symbol it is, and then you on some input, it will land in some another symbol, why I'm writing Q, say for example, say I say capital Q, one of the states, okay. That means if you have a state and you are on input, you go to another state which belongs to the Q, capital Q. That's a finite set of states, whatever states we have. But in case of this, it will land at the power state, and we know Q0, that's a start state, that belongs to the capital Q, that is the finite set of states, and we have a F, that is the final accepting states. It may be the set because the final states may be many. Now, how many states will be in the power set of Q? Because that can be equal to 2 raised power Q. What does that mean? Is if we have, for example, a Q that is the finite set of states. For example, we have 3 states A, B, and C. Okay, what will be the power set of Q? Power set of Q gonna be firstly the empty set. We can have an A, we can have a B, we can have a C, we can have then AB, A comma B, then we can have a set which consists of A comma C, then we can have a set which consists of B comma C. Okay, now everything is done. Now last thing is only left out, that is ABC. So a power set is a collection of all the possible subsets of the Q. So if it is 3, 1, 2, 3, so it will be 8. 1, 2, 3, 4, 5, 6, 7, 8. So if it is 3, it's going to be 2 raised power 3. Power set is 2 raised power 3. That's what we said. If we have a Q, whatever the length of Q is, that is here 3, and raised it power to the 2, that much of sets we have in a power set. So if it would have in A, B, C, D, that would be 4. So it will be 2 raised power 4. Power set would have 2 raised power 4 sets. So what we say is technically is that if you are on a Q and that means you are on some state, and you take some input, you can land it one of these, any of these inputs, any of these states. Okay, so that's why we say that if you take an input and you can land it with the power set of Q, that means any whatever the sets we have in the power set, any of the sets or many of some such states you can land into. Okay, that is in the NFA. But in DFA you can land it only in a one state. That belongs to the Q. Either you go to the A or B or C. You can have only three options, and only on one input you go to the only one state, and that belongs to the Q. That is A, state A, or state B, or state C. So if you have three states, 1, 2, 3. If you take an input, you can only go to the another state. Let's say for this is A, this is B, C. If it's A, you can only go to this state. Or if it's not in this way, if you want to go here, you can only go to this state, not to the multiple states. But here, you can go to the power set. Do you understand? Okay. Now let's take up some examples of NFA. This is what we discussed, that a binary string, any string which ends with 0 and 1. So it's like this. So we have a Q, that is the set of states we have is ABC. Input symbol is 0 or 1. Alphabet is 0 1. You can either have alphabet. You can have, this is a binary alphabet. You can have either 0 or 1 as an input. Initial state is A, and final state is C. So if you want to put, say, the transfer function, and then you see if you are A, this is transfer table here, you're going to have an input states here, and you're going to have input alphabet, that is 0 1, and also the epsilon here, right? In this case, if you're on A, you can go on 0 to the A, or you can go to the B, right? So it is a subset. On a 1, on A you can go to the A only, and on epsilon you go nowhere. On B on 0 you go nowhere. B on 1 you go to the C. B on epsilon you go to nowhere, and so on, right? So let's take another example where we say that, hey, you need to have a substring like 0 1 1 1 as substring. That means you can have up front something, you can have on a back something, not a problem, but you need to have in between your string 0 1 1 1. So we take up this, we say this state, if it is 0, firstly you go over here, if it is 1 you go to here, then you have a 1, you go to here, and then you again have a 1, you go to here, and then you accept it. And in the beginning, if you have the 0 or 1, no problem, and on here if you have 0 or 1, no problem. Okay, you can take any many 0 or 1s in the beginning, you can take any many 0s 1s in the at the end, but if you have somewhere 0 1 1 1 as an input coming juxtaposed together, right? So you take that string, and so you may have a bad choices where you for example, you had a string like 1 0 1 1 1 and 0 1, for example. So we have in between this thing. Okay, but you may go in a bad way also. For example, you say 1, you say this is state A, B, C, D, E. On 1 you can choose this path and stay on a A. Okay, so if you take this path, say you go on a A, and then you take 0, you may stay on a A, or you go to the B. But if you stay on A only, you can be here. Then 1, you stay on A only. Then 1, you stay on A only. Then 1, you stay on A only. Okay. Now after 0, you may go to the B. Say, or you may stay on A. Say for example, you go to the B. Then on 1, you go to the C. And input finishes, and you are not on the final state, so you reject this path. Okay. So excuse me. Okay. So you are rejecting this path. Okay. So if you because you may go this in a multiple ways now. Okay. And if you go in a right way, say for example one of the paths if that leads to the final state, then you accept it. We discussed already. So say for example, say 1, and you go on an A, then 0. If you chose to go to the B, then on 1 you go to the C, on 1 you go to the D, on 1 you go to the E, and after that you have zeros and 1s. Whatever you have, you stay on an E. On 0 you stay on E, on 1 you stay on E, so you're in a final state, so you will accept it. Okay, so you may have a bad choices to go, but if at least you have a one path which will lead you to the final state, then you will accept that, right? Let's take another example in which we say our input symbol, say for example, is I'm writing 0 and 1. Okay, and you can take many zeros and ones, and then we say that second to the last position there should be 0, second to the last position. So let's try to visualize the NFA simplicity versus DFA's complexity. Okay, because we say that NFA is much simpler than the DFA. If you see the non-deterministic finite automata machine for this, to build it is much easier. You say you are on a state, some state, initial state, say for instance Q0, then okay, if it is 0, you go to some state, say for example Q1, and after that if it is 1 or 0, it doesn't matter, because I say this is my last digit, second to the last position, because I want that whatever I have as a string, and but the second to the last position, this one, and after this here it could be either 0 or 1, whatever you like, and here it could be anything, no problem, but the last to the second to the last should be 0. That means I'm interested in only these two digits, right? Here, so I'm saying this is 0, you go on a state Q1, and here you can have a 0 or 1, or whatever you have, and you accept it. That is my Q2. Okay, so here in the beginning you can have either 0 or a 1 up front, so many zeros or ones, doesn't matter. But if on some 0 you go to the Q1, and after that whatever it is, the last digit, 0 or 1, only one transition should be there. It should not be multiple like this. Only one transition should be there. It could be 0, it could be 1, no problem. You go to Q3 because you have seen the second to the last is a 0, so you accept it. Now if you want to make a DFA out of it, okay, it's gonna be very, very complex. Let's try our hands on it. So we say firstly we are on a state, say for example Q0. Let me change my pen for this thing. Let me make it red. Okay, see, I'm saying this is my Q0 as an initial state. I should show it like this as well. Initial state should be always shown like this. Then say this is my last second last, and then I have the Q1, and I have if I have a 1, I will accept it as a Q3. This is my final state, right? It seems simple, but it's not that simple, right? Because this is not completely DFA. In DFA, we need to see on every state with every input. What are the alphabet we have? If you have alphabet 0 and 1, you have to see what happens on 0, what happens on 1, because you have to, this is deterministic machine, you have to tell exactly what will happen on a Q0 with the 0 or with the 1. Okay, so let's start from the Q0. If input was 0, no problem, you go to the Q1, and if it is so simple that if it is Q0, you have the input symbol 0, you go to Q1, and if you have a 1 after that, you go to the Q3 and you accept it. Okay, but now you have to see on every state what will happen to the other inputs. Say 1, if there is a 1, what will happen with that? Okay, because I can't go to the Q1 if it is a 1. So if it is a 1, I'm gonna stay out of Q0. That means many ones, whatever I have, how many ones I have, no matter how many ones we have in an input, let us stay on a Q0. The moment we have a 0, we have to go on a Q1. Okay, okay. Now on a Q1, if you have, say for example, an input 1, then you go to the Q3 and you accept it, and there's a final state. But maybe there is a 0. Okay, if there is a 0 input, what will happen on that? You have to see that also now. So if on a Q1 there is an input 0, no problem, because this will be the last digit, and this will be the second last. Okay, so that is 0. That's what I was searching for. The second last digit is 0. So that means if there was a 0, I'm gonna accept it. Okay, that's again the final state. So that is Q4 now. Actually Q3 now. The Q3 is also accepting state because this is my, if this is the last digit, this is the second last, that is a 0, so I can accept it, no problem. So I have done with the Q0, I'm done with the Q1. Now let me go on the Q2. Now on Q2 I am saying if I haven't seen any input, okay, say for example if there was a 0 input, what will you do to that? If it is a 0 input, that means last digit is now 0 and second last is this one, that is 1. So I can't accept it because second last should be the 0. So what I am doing is I am only going here. If it is 0, I'm going here. So I'm having 0, okay, I'm going here. So that means now for Q1 input is because if I was on a Q3 this is Q2, if I was on a Q2 and the input is 0, so I don't take it the last digit, I take it as the second last digit. Okay, so that's why I go to Q1 and try to see what will be the last digit. If it is last digit is 1 or 0, no problem, I will accept it. Okay, so say for example after that, if I have come here Q2 and I was a 0, I go back to the Q1 and now maybe inputs is 1 or 0, I will accept it, either Q2 or Q3. Okay, but I have to also see what will happen on a 1 if I am a Q2. So if there is a 1, okay, so that is gonna be my digit, but I can't take it as my second last because second last should be the 0. So I have to go back here to the start state, right? I have to go back here if there is an input 1, because this can't be my second last, because when I'm on Q3 I'm going back, I'm backtracking. Now what will happen is if it was 0, I can take it as my second last, okay, and take it these guys are the last one. But if it is a 1, I can't take it as a second last because my second last should be 0, right? So I go here, now try to see two states in which my second last can be 0, right? Okay, now these 3 states are done. Now let's go to the Q3. Now if I may have a 0, okay, if I have a 0, that's not a problem because this will act as a second last, okay, then so I will say okay, I will accept it because what will happen is this will be the last digit and this will be the this will be the second last digit, okay. And if it is 1, okay, so this will be the second last digit, okay, this will act as second last digit as a 0, so I will go here to accept it if it is 1, because this will be second last, okay, 0, but I can't come back to the, because if on 0 I'm coming back to it, on 1 I can't come back to the same, because then it will have a multiple things, okay. But I will do what, because on 1 I'm having accepting state this one as only 1, so I can go here, right? So now this completes my DFA, which has a 0 as a second last. Now if you see this diagram and this machine, so there is a complexity in the DFA, and in NFA it is much simpler to work, right? Let's take more examples now. Say for example we are seeing trying to see if on input symbol 0, 1, say for example we have, and we are trying to find all strings. We have a language L is equal to all strings over above sigma alphabet that have at least which have at least we have 2 consecutive 1s or 0s. That means we need to have somewhere 0 0 or 1 1, like that. If we have 0 0s or 1 1s, we're going to accept it. So we have to see the first this thing only we can draw that we have the 0 0s or 1 1s. Say for example we are on a first state, say for example Q0. Then if we have for example 0, we go to the Q1, and if we get another 0, we go to the state Q2. And if we have a 1 on this side, we take a 1. This is Q3, and if we have another 1, we go to the Q4. First let's build up the solution, then we try to so this is going to be my final state, and this is also going to be my final state because I am having the 0 0, okay. and up front I can have any many zeros or ones, no problem. And here I can have any many after that zeros and ones. I've got the 0 0, that's okay. I got the 1 1, I'm here, and after that I can have any many zeros and ones, right? What I'm saying is, if I got a 0, and after that if I have on this state, if I have a 1, so that means the death for this, because that means Q1 can't take after 0 any 1, right? Same is here, 1 you can't take after that 0, so that will be death state. Now what will happen is, if you have 0 and then 0, you go here. If you have 1 and 1, you go here, right? Now if we have, for example, this thing, we have A, B, so triple A, B, then I'm having B, A, B concatenating with the B, A, B star, right? Okay, so B, A, B, when I have a star, a clean star, that means it could be epsilon as well, so it could be absent also. So my minimal stuff is this thing, so I will start from a building like this. I'm on a start state, Q0, then on A, I go to the state Q1, on another A, I go to the state Q2, and another A, I go to the state Q3, so I got 3 A's, and after that B. The moment I got the B, I will accept it. Okay, I gonna accept it. So this is my Q4, that's my final state. So this is the minimal thing I need to have, triple AB. After that, it could have any many's BAB. So what I do is, after this, I could have if after this I have the B, because I have a B, I go to this state, okay, say Q5, okay, but this is not my final state, because after that I need to have B, A, B, or any manys. So if I have an A, I will go here, right, and then I have a B here, I accept it, because B, A, B, okay. Now it can go any manys, because after that, if I again the B, A, B, I'm gonna accept it, again I B, A, B, I'm gonna accept it. But if it's something else, I'm not gonna accept it, I'm gonna reject it, right? Let's take more examples. Say for example, we have AB star. What do you say about AB star? A, B star. That means A is there, but B is either optional, or there may be any many. Let's clean stars there. So what we say is, this is my A, the starting state. I go from A to this state, for example, this, and accept it, because B can be absent, and then there can be any many B's, simple as it is, right? What about AD? Now this is AND, okay, so that means I gonna have A. On A I go to this state, then I may have D, so there are two states here, and I'm gonna accept it, right? Okay, let's try our hands on more examples, and also we got to go for the Thompson's construction. Okay, we'll talk about Thompson's construction also later on. According to to build our from regular expressions to the NFA, right? This is what we are doing. We need to see some basic components as well, so basic building blocks. If you wanna build a house, you want to see which building blocks you have, so that you can put them together to build a big house, right? This is how we actually do in the Thompson's construction. We just take it as an example later. And to see the building blocks, say for example, if we have a transition of epsilon, so what we're going to do is, we have one state, say for example we've got one state, and from this state you have an epsilon transition, and you're gonna accept it, right? You may have a input, for example some single input, okay, maybe this is A. So what you will do is, you have a state, say this was state A and state B or something like that, or state Q0, okay. Now you have a transition on the A, and you're gonna accept it, okay. This is state Q1, so Q1 is my final state. Now this thing may be shown as, if we talk in terms of abstract machine, as an automaton, So we have a machine, for example, like this. This is my machine M, which has some final state which is accepting this input, right? Say for example this was a machine which accepts A, input A, which has like this, right? I should always put up the initial state like this, start state like this. Okay, does it make sense what I'm saying? And if we have, similarly, if we have some input B, for example, we got input B, then how we gonna have the machine? We have a machine, say M2, or say B machine, let me call it the B machine, which has some final state, right? Okay, now this was A, if we have single input. Now what about if we have AB, A and B, right? So we write it AB or A and B, dot B. This is the concatenation, we know that. So simple thing will be like this, that this is the start state and you have an A, okay, and after A you're gonna have a B input. If that is so, if you have an A and B input, you will accept it. This is your final state, right? This is the A and B. But if you want to do the same thing using a machine, that now we want to build a compound machine, because for us this was a one machine which is accepting A, this was another machine which is accepting B. So how we actually concatenate two machines, one who accepts A, one and another that accepts the B, right? So that is going to be like this. Say for example this was our machine A, which had a final state, right? But I don't want to make this as a final state now, because now from this we have a transition to the another machine, okay, say B, and only then I have a final state, and this is the epsilon move, where I move from a machine A on the epsilon transition, so epsilon move to the machine B. So I make it its final state. I will not make this as a final state, rather I will make from it this state an epsilon move to the start state of the B, okay, and then I will have a final state. So this is the same as A and B, right? Okay, now we move on to the A or B, or what sometimes called A union B. Okay, this is the union. In A or B, if we see it in a simple way, this is my A. Say for example this is my start state, sorry, this is Q0, and I'm gonna have you know, an input A, and I reach to some final state. Means if I have an A, I reach a final state, we accept it. But maybe if I don't have an A, maybe I have a B, then I will still accept it, right? So I can do A or B like this, okay, or this could be done like this, that we have an A state. Say for example this was an A state, that you have an A, this was start state, an A, and you are actually accepting it, okay, and maybe you had a B and you are accepting it, the same state. You had an A state or you have B, so you're accepting it and you make it a one state using the epsilon moves from the start state. So you say this is not my start state, it's not my start state, let I create a start state and have an epsilon moves, and this will be A or B, okay. Or in terms of machines, if you talk, then we will say this was, for example, machine A with its final state, but I'm not going to make it the final. This is the A, because I'm going to make a compound machine now, which is A or B. Now this is my B machine, which was having its final state, which accepts B, this accepts A, okay. Now I have a combined final state on the epsilon moves. This is how I do. And I will have a combined single state, start state on the epsilon as well. Okay, this is my start state. Now this will be my compound, so you write it like that, like this way or this way or this way. This is A or B. Okay. Now, what about A star? If we have, for example, A star, a clean star. Clean star means epsilon or any many A's. Okay, so that means we can have the absence of input. We can accept it, or we can have any many A's. Okay, so that means if I make a first start state and say, for example, I make a start state, and then I will say, okay, I will take an A and I go here. So this means compulsory I have sorry, if I don't make the final state is in start state, and I take an A input and go to here, that means compulsory I'm gonna have A. Okay, and maybe I will say, okay, after that I have any many A's, right? But this is not A star. Why this is not A star? Because look, this says at least I want an A. I go here, I accept it. This is 1A, I accept it. After that I have 2 A's or 3 A's or 4 A's, no problem. But at least I'm gonna have a 1A. So this is not actually A star, this is A plus, right? Because which says that we have at least one instance. So A star actually means that we don't have even a single instance. And maybe we have epsilon also. So that means I will make my first state as my accepting state. That means if I don't have any input, so I'm going to accept it. So that is what epsilon means. And then after that, I'm going to have any many A's, whatever you like. So this is actually the A star, right? But if you're trying to build it, for the Thompson's construction, I'm saying that we want to build it from the basic building blocks. That we had a building block like this. For A, we had a building block like this, right? For A, we actually have a building block like this. That is a start state, and I am having A, and I got a final state. Now I want to make from this A star. This is the representation of input A. Okay, not A star. Now from this I want to make the A star, right? Then I would do like this. That I will take up this state. If I say firstly a machine, say for example in terms of machine I'm talking. So this is my automaton A, and this was its accepting state. So this is representing a machine which accepts A. Okay. Now if I want to make A star from this, then what I'm going to do is I will say, okay, this is my A. Now don't make it as a final state but initial state, because I want to make it a compound machine now, which takes the single epsilon and any many A's. That's A star, right? Okay. Now what I got to do is I will make firstly an epsilon transition to the final state. So this is not final state. I will make this as a final state. I can do same with this also. I will show you in a while, but let me do it for this machine A. That I'm saying, hey, that this was a machine A. Say maybe usually we write it in a capital A, which was taking an input A, and I'm not making this as a final state. Rather, I make it a state which has a transition, epsilon transition over a final state. Now I need to also have a start state, right? Maybe you say, okay, this is my start state. The A already had a start state, but the problem with this is that you will at least have an A as an input. It is like what I did on upwards, like this. It will be like this. So that means I'm having at least one A as an input here. So I am missing out the epsilon here. So what should I do? I should do one thing. I should put up a start state, separate start state. Okay, and this has an epsilon transition with this machine A or automaton, right? Then to accept the epsilon, to accept the epsilon, that means absence of A. That means from a start state I will have a direct move to this guy, final state on an epsilon. That means if this thing is missing, okay, if this thing is missing, I can still have a from start state to final state on epsilon. So I'm having the epsilon now. Okay, so in this diagram I'm having the epsilon from this way, and I'm having a single A input from this way. What about A star? A star says that you have an epsilon and you have any many A's, right? So that means you should be able to take input again and again and again. So for that, what we will do? Okay, for that we will do one thing. We will go from here, okay, into this state on an epsilon. So after taking A, I may go back and take A again. I may go back and take A again. Okay, and at any moment I go to the final state, right? Or you could have done it from here also, that you are from this state and you have still A and you go on. Okay, so better is from here, because if I have, for example, 5 A's, I go to this from start state, I go to from epsilon to this A, I take input A. This is the machine which takes input A. This is actually this machine which takes input A. Then I go back and epsilon transfer and take A's again, any way I like. Or if I don't want to take any input, I can go from start state using epsilon and go to the final state. So this is the perfect picture of A star, right? So what about if I want to do it using not a machine but simple transition diagrams? Okay, then I will say like this. I will say it like this. That will be more explanative actually. That will give you more explanation to this what I was talking. We say that, hey, this is my input, okay, A, and we go to the some state. This was final if I want to take only A, but I don't want to take only A, but I want to take A star, right? So what I do is I go from here on epsilon transition to some final state. Okay, now this is again something which takes single A input. Now what about if I want to take the epsilon? So I want to make the start state separate and have an input to its start state, A's start state, and from this I will have an epsilon move to this. Now this machine will take either no input, say for example go from start state into the final state using the epsilon move, or if you want to go this way, that means you are taking single A input. Now what is missing out is multiple A's. So here, from here, you can do one thing. You can have an arrow from this. After taking A, you can go back here on an epsilon move, or simply you can go back here using epsilon move. And from this state, if you want to take more inputs, go here, get back, go here, get back, go here, get back. Okay, so you can, this is the epsilon transition as well. So you can go back and forth and take any many A's you like, and when you are finished, you can go on epsilon move to the final state. So you're accepting it. So this is kind of A star, right? So in Thompson construction, we actually are trying to build the complex regular expression using our building blocks. Before we move exactly into the Thompson construction, you may have understood it, but I would like to do more examples so that we'll be stronger in the NFA, okay, NFA construction. So let us take more examples. What about taking a very simple thing, A and A star? This is equivalent. This is actually equivalent to A plus, right? That means at least you have one A and then you have A star. I will take this is my start state. I will have at least one A to go to the final state, because if I have the A and I'm going to the final state, and after that, because it's A star, this may be missing, okay, because this may be epsilon, so this may be missing, or this may be any many. So if it doesn't exist, I have only single A, I'm getting it, I'm accepting it. So that means this was this A, okay, and this one was epsilon, so this was missing. Or this could be any many, then that means I can have here any many A's, right? So at least I have one A, and at most I can have any many as I like. Does it make sense? Okay, this was A star. Let's take a more example. Say for example we got we saw the A and B. Oh, where is the pen? Okay, here is it. We will say A and B concatenations, but star. Okay, what do you do to this? When I say star to the whole, that means it may be missing. Okay, it may be epsilon. Okay, or it may be any many. Now when it's epsilon, that means whenever I have a star as a whole, that means the initial state is going to be the final state. You just remember it now. Okay, because it may be totally missing. It may be epsilon, so I can take it. After that, I'm going to have A and B. Okay, so I'm going to have A, for example. I move on to this state. After I have an A, I need to have a B. The moment I have A, after A I have a B, I'm accepting it. Okay, and this can go any many times. Okay, this can go any many times in a loop. So you can go single time, multiple times, and epsilon times, no problem, right? This is Q0, this is Q1, and so on. Okay. Let's take up little more examples, there's little complex ones so we understand. Okay, but if you do it using the Thompson's construction, what do? You will try to build for the A, then for the B, then A and B, then you try to think of star. We'll discuss that in a proper way a little later. Okay, that will be actually the climax of our this lecture. Okay, now what about A star or A B whole star? So look at this. This is a star on A, or means a union, and now it's a concatenation, but it's again the whole star. So that means the whole thing may be missing. Okay. So if I say firstly the A star, let's talk about the A star. What is the A star? A star is like this. Is it missing or many times? What about the AB star? We just did it. We said AB star. Okay, it's AB star. The first is going to be the accepting state. Then on the A it goes here, and on the B it comes back. It's accepting. Okay. Now I want to combine them, order them together. So how we union? We make one single start state, epsilon transitions to the both of these guys. This is how we work. So this is A star, this one, or AB star, right? Like we had A or B. On the top we did A or B, right? We did why we did A or B. This is why we did A or B. Okay, you can visualize this one. You have an A, you have a B, then combine final state and combine initial state, right? Now for A and B we had A star and AB star, right? We had A star and AB star. So this is A star, AB star, combined initial state. Okay. Okay. You can also do here. We had a multiple final states here. We can do that, but we can also have a combined final state and have an epsilon transition from this to that. Okay, so that will also make sense, right? Isn't it? So we'll have combined final state here, and this will not be my final state. This will not be my final state, and epsilon transitions from this to this. So that is one the same thing. To make a compound machine with single final state. Okay, you can do that also. Okay, now I will move on to the next example. Let me make it AB or ABA whole star. Now star is to the whole. Now I got firstly the AB on this side. It's the same as you can do it like that. Same. You have an AB and then you have an ABA. So you build it for AB. So what is AB? Actually, this will be AB star because star is on the whole. That means star to this and star to this. So what about AB? So this is gonna be firstly the final accepting state. Then I have an A and I have AB. That's it. On the bottom I got an ABA. That means, and that to star. So I will have an accepting state. I will have an A to this state. Then from this state to another state on a B, I move to the B state. And from this I move ABA, so A to this state. Now I combine them together using single epsilon transitions from a single starting state, right? Okay, so this is gonna be my AB or union ABA star. Or I could do one thing. I can make as a single final state epsilon transitions to that, right? Okay. Let's move on. What about very simple thing, A or B whole star? Simple, A or B whole star, right? So that means firstly this is A or whatever inside is, because the whole star, the first will be the accepting state. After that it may be A comma B, A or B, no problem. NFA is so simple to make, right? One more thing, if I do a little change also to this guy coming in my mind this time. Yeah, this guy. Let me change my pen. Make it red. So that will be much better visible. I mean, okay, so because I'm having a star here and I'm having a star here, that means actually the whole star. So I can actually put it like this also, that this is my accepting state, because both of the guys are stars. So if anything is absent, no problem, we can fix it, because if this is absent, no problem, it's equivalent to whole star, right? So after that, if I have an A, okay, and accept it, or any A's, accept it. Now you may ask a question, hey, is this A dot A star, or it is A star? But I will say this is A star actually. Why? Because this is the accepting state. So if you don't have, you accept it. You have a single A, accept it. You have after that multiple A's, accept it. So because we have for epsilon here, okay, if you don't mix it with like this, you have a starting state, an A, and accept it, okay, and after that you have an A. This is A dot A star because you have a one A. After that you have any many A's. This guy is actually expansion of A star, because if you say A star, we could have done it like this, okay, but because I am this is the A star, if absent or any many A's, but here I want to combine it with the AB, so that's why I'm making this as a accepting state. And this is also the star, so this is same for this guy also, so it will become a little simpler. Say this is A, okay, I'm going here, and if after that I'm gonna have a B, okay, I can accept it. Why to go on that side? I can draw here the final state, that's my B, it's accepting the B, and to make it an any many times I can come back, but I don't want to do this, right? That will not be a good thing, so I will do like this, B. Now if AB is absent, no problem, but if there's AB or any many ABs, it's gonna work fine. So we can do it like this, we can do it like this. On epsilon transitions, you go here and then A star, so you go here and AB star. This is the AB star, this is the A star, right? Does it make sense what I'm saying? Now let's try our hands on more examples, okay? Say for example, we have something which starts with the, when I say it starts with 1 to 1 1 or something, it starts with 0 1, or it starts with A, or it starts with A. That means in the beginning I'm having that much. Say for example, I say that I am starting with the AB, for example, A and B, or I may say I start with the 1 and 0 or something like that, okay, in a binary, or this guy. So after that means I'm starting with this, and after that I can have anything, whatever I like, right? So what I do for this is when I say starts, that you will have a start state, and then you say, hey, I'm starting with the A, then I start with the B, okay, after I gonna accept it, and after that whatever it is, A or B, I gonna accept it, right? Same you do with this. So you will say here 1 and 0, that start with the 1 0, and after that it may be 1 or 0 or anything, any many times, no problem. Similarly, if we say at the end that I'm ending with the AB, or I'm ending with the 1 0, let me take it now AB now only, right? This same as 1 0 or something, but I'm ending with the A comma B. That means what I do for that is that I say, okay, again I will say like this. In the beginning I say, hey, if I have any diamond thing, I don't care is it A or is it B, but I should end my string with AB. If I'm having such thing, I'm gonna accept it, okay, right? Sometimes I say that, hey, I want to be, this is a substring, means it should be contained within my string. Like for example, I have something A, B, B, A, whatever, but somewhere there'll be A, B, and after that it may be in the beginning may be anything, it may after it may be anything, right? So what I say here is, this is my beginning. I say, hey, in the beginning, whatever it is, I don't care. This is my start state, okay, but after having whatever I have up front, then I have A, then I have a B, okay, and after that I'm gonna accept it, but After that, whatever it is, I don't care, right? A comma B, I'm gonna accept it. I'm finding something in between A, B, and after that, whatever it is, I don't care. Okay, I'm gonna take it, right? This is something which contains A, B. Okay, let's take more example. Before that, I just want to change my pen back to green. I don't like red, I love green. That's as simple as it is. So what I'm saying is that a question from a book which says accepts all, NFA which accepts, I'm not good at writing, all binary strings. Okay, where, let me write it and then, okay, here we go. Then I'm saying NFA that accepts all binary strings where the last symbol is 0, or, now concentrate on this or because it's a union operator, okay, that contains only ones. So I can have the last symbol as 0, the last, which I just saw here, like the last, like it contains the last guys of these, okay, up front whatever it is, but at the end I should have the last factor as 0. Here it was AB, but I could have only 0, that means this much, okay. And or that contains only ones, that means on other side I have only ones. So if I say on the 0 side first, that I can have a thing and then I have a 0, the last, okay, symbol is 0, I accept it. But that means in the beginning I can have anything, whatever I have. I can have a 0, I can have 1, because the binary, we can input alphabet is 0 and 1, and so up front I can have a 0 or 1 or any many you like, but at the end I have only 0, right? This is one thing. The second thing says, or that contains only ones, which contains only ones, or that means kind of 1 star. It means kind of 1 star. That means it contains only ones, okay? Or that means if there is no one, then that means it may be absent also, or it may be any many ones. So that means either this or this. So if this is absent, no problem, we can go on to this side where I say that I'm having only ones, or maybe it may be absent as well, right? So I'm gonna accept it. Now how I combine them? Simple. How we do OR? We have an epsilon transition from a single start state, and that's it. Okay. Okay, now this is an NFA for a language that we have an input symbol of ABC. Okay, alphabet is ABC that ends with AB or BC and CA. Okay, so that means this is the AB, BC, CA. It ends with. In the beginning, you could have anything A or B or C, right? Okay. One correction here is actually OR, because I didn't AND it, I did OR. Okay, if it is AND, then this is something a different story, because in concatenations we do different things, right? This is the OR. Okay. Okay, now it's time to take up the Thompson's construction, which is actually an kind of algorithm which transforms regular expressions into equivalent non-deterministic finite automata, right? So in this case, your input will be a regular expression or over some alphabet, and the output is going to be in some NFA N, which actually accepts that language where we have that expression R. Okay, so it is, the algorithm will work actually recursively. How it will split the expression into the constituents and sub-expressions, from which the NFA will be constructed using a set of rules. We will have discussed already those rules, and it actually builds a parse tree, and then in that parse tree we have the subunits, and those subunits will be according to these rules. For example, if we have an empty expression, so simply we have the from a state Q, start state with epsilon, to the final state you have an input A. We have already done that. Okay, if we have an union, okay, then we know we have a machine which is accepting the S input, for instance S or T, and this machine accepting T input, and we combine them by converting their final states to the state with a transition to an external final state. It's a combined machine now, and these start states will also not be now start states. They have the epsilon transmission transition from the Q, so this will be the combined start state. Okay, and similarly things go for the concatenation, that the final state becomes the initial state of this machine, and they combine together with this. Its initial state will be the initial state, and its final state will be the final state, right? The T's final state. Okay. Then we have a clean star. We have already done these things that we need to make it many times. So this is something which accepts S. Okay. So this is the final state. So I don't say final. I put it epsilon trans to this one, and then I will take many internally epsilon trans and get back and get that input S many times as you like. Or you could have gone from the initial state to the final state using an epsilon move. So that means the absence of the input. Okay, that is the S star. And we have already done all these things, and we should remember that the new NFA has at most twice as many states, because for any operation it at least have two states, right? Say for example here was the any input, say for example like this epsilon or A, we have at least two states, so it will have at most two states. And in case of concatenation, at least states become a little lesser, because they combine the states of these two guys. Its initial, its final and its initial is combined into one state. So at most there will be two states, twice as many states as whatever components we have. Okay, and the new NFA will have a one start state and one final state for sure. Each state of a new NFA has either one outgoing transition on a symbol S, or at most two outgoing transitions. So you may have transitions either one, or you may have two transitions, but not more than that. Okay, this is to be remembered. Then this is the basic Thompson's construction, but you can later on do smart parsing, and wherein we can improve our Thompson's construction, because if we have A double star, so this will be actually A star, right? So this will have a minimal states, and accordingly we have these guys where we have simplified things, and you can have many more other than these where we can simplify our basic Thompson's construction. Okay, now let's take up some example and try to see how it works. Okay, say for example we have an expression. I have got a pen. We have to be green. Okay, say for example we got an expression A and B. Okay, then actually you OR it with the C, and then you do a star of whole thing. So what Thompson construction does is it will break it into the individual sub strings, okay, sub expressions. Say for example here, let me choose a pen here with something like I will use a red pen. Okay, so it will convert this firstly into this. Say for example, let me call it R1. So this is A and B. So if I try to build it on the side, say A and B. So we have firstly having an AND operation, and there is an A and there is B. Okay, maybe this will be called as R1, and this is called as R2, and this will be called as R3. So you calculate first R1, then you calculate R2, then you calculate R3, compute actually, then you're gonna do like this. So this is kind of an parse tree. Then you have a C that will be called R4 maybe, and so on, and then you have an R which you do with these guys. So let this be called as R5. So similarly you're gonna build your parse tree, and then when you are done with it, you have a star. Okay, you do star with this R5. Okay, and that will be called R6. So R6 will be your final NFA, which will do star to all of these guys, and so on. So let's calculate now this. Let me write it again. Try to hold it. I'm saying I have gotten A and B or C whole star. So how I gonna do it? So firstly, I will break this into the R1. The R1 is actually what? Actually R1 is this A. Try to see the basic rule for A. This is R1, okay? So if I write on a side, this is my R1, and what it's gonna be, it is from state, say, so for example Q0, start state. You take an A input and you go to the state Q1, right? And this is gonna be the final state. This is my A. Okay, does it make sense? Now similarly, we have the R2. This is my R2. So what is our R2? R2 is the same thing. Only difference is now I have, maybe I will call it state Q2, and I am using the B to go to the final state and call it Q3. Okay, Q0, Q1, Q2, Q3. This is B. Now after I'm done with the A and I'm done with the B, now it is time to do concatenation of these two guys. So that will be called as R3. So R3 will be actually both of these guys, right? So this is R3, which is doing AND of R1 and R2. So what is my R3? Let me write it here, R3. So R3 will be this is doing the AND of this and this. So what is AND doing? AND will combine its final state and its initial state into one state, right? And this will be initial state and this will be the final state of the combined machine. So this is your initial state. Now Q0 is going to be your initial state, right? Then it will go by the A to Q1. But this will no more be a final state now. Okay, and this will be merged together, and so Q2 will be no more. So on a B, it will go to the Q3, and Q3 is going to be your final state in this case, in R3, right? Okay, now we move on, and we're done with A and B. Now it is time to do with the OR with the C. So before doing OR with the C, we'll try to see what is C. So my C is gonna be the R4. Okay, let me try to write it. R4. So what will be R4? Okay, R4. Let me write it here. R4 is gonna be C. Okay. So I have a state. Let me call it Q4, I guess, because I have 1, 0, 1, 2, 3, yeah, Q4 as initial state, and it takes a C and it goes into a state called Q5, and that's going to be my final state in this case. Now I do the OR with R3 and R4, right? Because R1 and R2 were AB, dot was the R3. Now R4 is C, so R5 will be the OR. Okay, so R5 is gonna be the OR. Let me, where's the pen? Okay, here it is. Now R5 will be this whole thing. Okay, now how will we draw our R5? The thing is OR. OR does what? We have learned it, so it's not a big problem. So we say that we have to do OR of what? But you know, R5 is the OR that is of R3 and R4. This is my R4 and this is my R3. So I combine these two machines, okay, using the epsilon transition and make a combined start state. Okay, and also we should remember the rule here. which says has one start state and one accepting state. So you can't have multiple starts and multiple accepting states. Okay, so that's why we have to combine the two. So we are going to combine this and this into the one state. Let me make it here. Let's make it here. So this is my R4, which was having what? This is having Q4 and taking C as an input. It goes to the Q5, which was a final state, but now it is no more a final state. Okay, because I need one single final state. Okay, and one single start state. And this is my R3, which was having like this. You're saying Q0, A, Q1, and Q3 on input B. Okay. Now what we do is that this was the final state. So this will no more be now a final state, and these two will no more be a start state because we need a single start state on epsilon move. This is what we do when we have an R. We have learned it already. Call it Q6. Okay. Now this will be R5, right? Okay, and this will have an epsilon move, and so that this is an epsilon not E, so that we have a single start state, and we're gonna have a single final state as well. Okay, on the epsilons, move on epsilon to get a single final state, and let's call it Q7. Okay, Q7. This is Q7. Okay, this is Q7. So this will be my now combined machine of this much. Okay, here this one R5. Now what about star? Now we have left out with the star, right? And now what we have to do here is R5 star, simple as it is. Now we have to do R5 star. This is to be done now, right? So R5 already here. R5 is already here. Okay, now you have to do star. Star means what? So star means if I have to do R5 star. Okay, R5 star means if it is here, it can be epsilon. So this may be totally absent. So for star we add up another start state, which is an epsilon, and a final state. Okay, we add up a start state on the beginning and a final state on the end. Firstly, let me draw this, and let me draw this in the different color so that it's more visible. So let me this is the Q0. Let me draw it. So I have drawn the same thing here, as you can see. Only difference is this was my start state here, by the way. So, okay, and this was my final state. So I have removed this as a start state, I have removed this as a final state because I want an other state called to be final state. Okay, it's my final state, and let it be Q9. Okay, and on epsilon transition, and I will add up a start state also here. Epsilon transitions in the start state. Let it call it Q10. Okay, whatever. So now the star means the R5 clean star means that there may be the epsilon, that means no input at all. So that's why I can go from start state to the final state, right? So without taking the input. So maybe R5 is totally absent, and R5 also means that it may be many times R5. So this green part is the R5, right? So what I do is to repeat my thing, I go from here to the back to the Q6 so that I can take it this kind of input many times. Now this is my the final NFA using the Thompson's construction. So if we check our rules, we say that one starts in one final accepting state. Not more not more than two outgoing transitions, and at most twice. If we see how many actually I have chocolate in my mouth. Let me finish it. Okay, done. I'm saying we have 1, 2, 3. When we count the operators, we don't have to count the parentheses. So we have 1, 2, 3, 4, 5, 6. So 6 into 2 is 12. So at most we can have 12 states. It will be lesser state because we have concatenation that will make it lesser. So if you see, it's a 9 states. So that means in fact we have 10 states, I guess. How many states we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 states we have. So that's lesser than 12 actually. So we can't have more than 12 states in this, right? But when we do improvements over Thompson construction, we can reduce many states as well. So let's take up few more examples. Let's have for example a regular expression a or b whole star times a. So this will be my R1, right? What will be R1 doing? So R1 is simply having state, start state, let me call it a 0 state, okay? To the take an input A and go to state 1, right? And this is your final state. And what about this will be R2. So R2 is gonna be from state 2 as start state, take B input and go to the final state, call it 3. Okay, now then there is gonna be the OR, the union operation. So let me call this whole thing as R3. So what is R3 going to do? So R3 is actually OR of these two guys, okay? That is A or B, or these two guys, right? So how I do that? So I will make the above one on the A0, go to the 1 and don't make it a final state, right? Similarly on the downside I have the 2 on taking B goes to state 3. Don't make it a final state, make it combined final state now. Call it state 4 on epsilon, and have a combined start state, call it 5, and on epsilon moves, and this is your new start state. So this will be the OR operation. Now you have to do star of this whole thing. That means you're gonna do R3 star, right? R3 star. So how we do R3 star? We know that we have to use the new final state and new initial state, and also try to see many R3s and also the epsilon. So we already know it, so we can do it much easily. First make this guy again. We have this thing, and if I rub it, so if I make it as my single state, this is not a final state, okay? So add up another state with the epsilon, go to the state final state, call it state 6, okay, and have another state which is my start state, right? Don't use this as a start state, go on epsilon on this, and call it state 7, and from this we can have an epsilon move on the final state, so that there may be the absence of the input, and you have to go for the repetition as well. So from this state to this state have an epsilon move, so that you can do it many times, right? So this is your R3 start. Now at the end you need the A input, okay? Right, so whatever here we have the R3 star we did, right? Now R3 star will be this thing, call it as R4, and now you do AND it with the A. So this A will be R5, then at the end you have to do R4 and with R5, right? So how we do that? So firstly, if I say R4, that is my state, I'm taking input A, go to another state, that's its final state. So let this called what state it is, it's 8 and this is 9. Now combine these two guys together, right? Only difference here will be to add up the A on this side and make this as its initial state. Cancel this as a final state. Okay. Let me do it here only. You can do it in a much better way. Then I'm saying make this as our state, not as a final state. And now combine these two guys. When you do AND, you are combining the final and the initial of these two guys as a one state, that is this state, and then on A input you go to some state, that's a final state. This final state will be the final of the whole machine. Now call it state 9, it's a state 9 already, right? Rest is same. So this will be the final NFA for the regular expression, this one, A or B star times A. Let's take one last example, that is A or B whole star A B B, right? So how we'll do it, this is my R1 and this is going to be R2, and combined together will be R3. Then doing the star of it, R3 star will be R4. Okay, now this will be R5, this will be R6, this is gonna be R7. So do the concatenations of these, maybe these two first, that is R8, then this with this, then that's gonna be R9, and then what you do is do the final AND with R4 and the final AND with the R4 and R9, right? This one, call it R10, call it R10, right? So this is simple, I guess you can do it now with an ease. You have an A, then you have a B, then you OR them together, then you star them, then you do on the one side A, B, B. Okay, first A, then B, then AND them, then again AND them with the B. So that will become A, B, B. Then AND them together with this, that means its final state and its initial state, combine them together, and its final state will be the final state actually, right? I think you can do it with an ease. So that's all for this lecture. See you next time in a next step wherein we go from now NFA to the DFA. Okay, see you next time. Maslama.